This lecture is going to cover the details of the k-nearest neighbors algorithm. So I gave you an idea of the general gist of how kNN works, but there's some key questions to be answered before we can actually use it for classification. So the first one is, how do we actually represent points as data? The second is, how do we measure the similarity between 2 points? Then once we've found the k-nearest or the k-most similar neighbors to the point of interest, how do we combine them to make a classification? And then finally, how do we determine k, or how do we figure out how many neighbors we should use? So step one is to figure out how we're going to represent our data, represent our instances as data that can be read by a predictive modeling algorithm. And so as a reminder, each data item is represented as a set of attributes. So each instance is represented as a set of attributes. And then we can turn that set of attributes into a feature vector. And so here in this beer data example, I have two example beer drinkers. I got their pictures from a Google image search. The guy on the left we'll call John. We have his age, income, his gender, and whether he's married or not. So remember, in this data, male is encoded as 1 and female is encoded as 0 for gender. I thought it was funny, the stock image label for this picture is for tough macho beer drinker. So he's a regular beer drinker. And then on the right-hand side, we have Rachel, and we have, again, her age, income, gender, and marital status, and she's a light beer drinker. Right, so we turn these sets of people into sets of attributes, and the sets of attributes into feature vectors. Now it's a set of numbers that can be read by any standard predictive algorithm. So step 2 is to quantify the similarity between pairs of points. And so what we're actually measuring is the distance. And usually we'll use the Euclidean distance. So the Euclidean distance, this you might have seen in high school math, but it's the hypotenuse of the right triangle formed using points A and point B. The Euclidean distance between point A and point B will be the square root of the sum of the squared differences between each of the coordinates of point A and point B. And so with 2 features, we can think of each instance as an object in 2D space, or point in 2D space. The coordinates are the values of the features. And then, this is the formula for Euclidean distance. If we wanted to add more dimensions, we could just add more terms inside the square root. So if we had a z coordinate, then we'd also add plus zb minus za squared, and so on and so on. There are also other geometric distance measures, like the Manhattan or taxicab distance. The L1 norm is another one, right? There are other geometric distances, and then there are also more specialized distance metrics that you can use if you have categorical data. For instance, the Jacquard measure is a categorical distance. But for now, in this class, we'll use Euclidean distance, and as usual, you won't have to calculate this by hand in practice, although I might ask you to calculate something like this on a test. And so let's go back to John and Rachel. So John and Rachel have 4 features, so they're each represented in 4-dimensional space. And so to calculate the distance between John and Rachel in this 4-dimensional space, we'll take the square root of the sum of the squared differences between their individual feature values. And so you might notice something wrong with this calculation, or something kind of questionable about this calculation, which is that all of the variables, or all of the features, are on different numerical scales. Right? Age ranges between, let's say, 0 and 100. Income is in 0 to hundreds of thousands of dollars. And then marital status and gender are categorical or factor variables, so they're binary. And so the Euclidean distance is going to be disproportionately weighted or disproportionately affected by the income because it's on the largest scale. And so oftentimes we'll use some form of data preparation to compute the similarity. And so we usually normalize our features, especially numerical features. There are two usual ways that normalization is done. The first one is to give everything the same mean and standard deviation. This is also called z-score normalization. And to do this, we'll subtract each feature by its mean and then divide by its standard deviation. So this will give everything a mean of 0 and a standard deviation of 1. We can also give everything the same exact numerical range by subtracting each feature by the minimum value that it takes on and then dividing by the range. That will put everything between 0 and 1. And either of these are acceptable, but usually if you have a bunch of variables that are on different scales, we have to do some normalization in order for kNNs to work well. And so let's go back to the kNN algorithm. So for each new point that we want to classify, we'll find the k most similar neighbors, combine their values somehow, and then use those resulting values to classify the point. And if we have 3 points, let's say we're doing 3 nearest neighbors, if we want to classify point A, we find the 3 most similar points to point A. So these are circled are the 3 points that have the smallest Euclidean distance to point A. And then somehow we'll combine them and use that combination to make a decision on not on what the point's predicted value is. So I guess the next question is, how do we combine those neighbors? How do we combine them to decide the value for each new point? And so let's remember that light is coded as the positive class or the 1 class in our data. And to estimate the probability that y equals 1, we'll usually just take a simple vote based on the neighbors. So in this case, if we have 3 nearest neighbors, we'll look at the average score, the average label of the 3 neighbors. And so the probability that person A likes light beer is 1 out of 3. 1 out of their 3 nearest neighbors likes light beer. For person B, the probability that they like light beer is 2 out of 3. 2 out of their 3 nearest neighbors like light beer. And then for person C, it's 3 out of 3 or 100%. All 3 of their nearest neighbors like light beer. Right? So we take a vote and we take the average of their votes to get the estimated probability that they prefer light beer. Now, once we have these estimated probabilities based on their set of neighbors, based on their set of 3 neighbors, we turn that into a score, right, by getting the average vote. And then we can use a cutoff to do classification, just like we've done with all other methods in this class. So the default cutoff of 0.5 results in the majority vote, or taking the majority vote of the nearest neighbors yields what's equivalent to setting the cutoff to 0.5. And so for examples like this, we often choose odd k values to avoid ties, right? We don't want to have two neighbors in one class and 2 neighbors in the other class. Then there's some ambiguity about what we decide for the classification. We can also choose other cutoff values to change the classifications, just like what we've done with other classifiers, right? So if I increased the cutoff to 0.75, then point B would no longer have a predicted classification of 1. If I decreased it to 0.25, that would change person A's classification. It would change it from 0 to 1. Right? So we can change the classifications by changing the cutoff, just like we have with trees and logistic regression. We can also use kNN to perform numerical regression, not just classification. For example, if we're looking to predict the ages of instances based on their neighbors, so numerical variable, we just compute the average age in their set of neighbors. So it works very similarly. The numerical prediction is just the average of the numerical y values for the neighbors. One last thing to consider is whether we want to count all neighbors' votes equally, right? So consider the starred instance. It's kind of down on the bottom here, down on the bottom in the middle. If we were considering all neighbors equally, let's say we're doing 10 or 11 nearest neighbors, we'd end up counting the nearest neighbor as important in the voting as the 10th nearest neighbor, right? So that doesn't necessarily make sense. We often want to count closer neighbors as being more important in the vote. And so we can apply a weighting to nearer neighbors' votes to weight them as being more important in the final calculation. And this technique tends to work well for regression. So using these weighted distances works well for numerical regression or for predicting numerical target variables.